million tires are scrapped every year. And 80% of those are currently recycled, but that still leaves 60 million tires a year that are going to landfill. So can we do something with this material? We have an industry partner that is taking this recycled rubber clump, and they're cryogenically breaking it up into a microfine powder that we're able to 3D print with. And one of the interesting things about the rubber, even though it's pulverized to the same size as the wood or the cement or the paper, each material has its own inherent properties. So when you 3D print something in wood, it comes out of the printer hard, but when you 3D print with rubber, it comes out of the printer pliable and a little bit spongy and soft. Plastic. So this isn't a material that we have invented, but we do work with companies such as MakerBot, and we are helping them develop examples or case studies for how end users might use their machines and their materials, this is PLA, to make things for architecture in the built environment. So this is a 3D printed block that we've printed out of their translucent orange, and we also 3D printed the connectors which hold the blocks together. So in this case, it's an opportunity for MakerBot to say, you don't have to make just little tiny robots, right? You can make architecture with these machines. And we also partnered with them to make this 3D printed dome, which is called the Star Lounge. The challenge here was to develop a structure that they could print, and we had to really think about file management. So for us, it's not an issue to say, oh, there's 1,000 unique files. Well, that's okay, we'll print them. We didn't want to send them what in the end was 2,500 unique files. So we worked really hard to develop a structure that would have a very small number of unique pieces. And in the end, I think there are only 27 unique hexagons that make up this structure, and they're color-coded, so all of the blue ones are the same, and the white ones are the same, and the orange ones were the same. And we made a little booklet for them so they would know how many to print of each one. So the piece, as you saw, is actually componentized. Oh, sorry, I won't make you watch it again. There are the 2,500 individual hexagons, but those hexagons are all riveted together to make these larger hexagons and stars. And that makes it transportable so that we can move it from site to site, and it can be erected in a matter of a few hours. Another thing to note is that it's incredibly lightweight. It weighs less than 200 pounds. The hardware weighs almost as much as the plastic does. Each of the hexagons is only 1.5 millimeters thick. So I think thinking about issues surrounding sustainability and how much it costs to transport things, how much time it takes to make things, there's an opportunity to have an impact here. Here's some views of the interior. So you can see the light coming in through the holes in the center of the hexagon, dappling the ground. And the PLA is translucent, so it's very beautiful, and it glows when it's well lit. Salt. So you've all seen the salty glue. So this is a local material for us. It's a renewable resource. It's incredibly inexpensive. And when 3D printed and post-processed with our polymers, it's very strong. And one of the nice things about the salt is that it has beautiful optical properties. As you see in the exhibit, it's translucent. So it doesn't have to be printed as thinly as the wood or the cement. It can actually be a little bit thick and the light still passes through it in a really beautiful way. And we've experimented with different ways of interlocking and aggregating these salt blocks. This is a building designed by Tom Faulners, and we 3D printed a salt model for him. This is a view of the crystallizers in the South Bay, owned by Cargill. And at one point, over 1.5 million tons of salt was excavated or was shipped from the bay each year. And it's not that much now because Cargill has sold 16,000 acres back to the government so that the land could be returned to its natural habitat. And they also set aside 1,400 acres that they would develop for 12,000 houses, about 30,000 people, which raised the question, could we build houses out of salt on this land? Again, can the material source and the building material itself be seamless? So we designed the salty glue that's made out of 336 or so salty tiles, which were inspired by salt crystals, the forms of salt crystals. The overall form of which was inspired by these very traditional baskets that were used in the salt extraction process to come up with the salty glue as a full-scale study model for thinking about architecture and salt in the South Bay. And here you can see, again, those really wonderful optical properties. And this is just from the natural light coming in through the window. There's not a light inside the salty glue itself. This was one of the first large projects that we built. And we were still in the early phases of thinking about how these tiles would connect one to another. So if you've been over to the exhibit, you probably see that they're binder clipped together. And we've moved on from that method of connection. But it was a really fast way to mock this up. So, as you're making things in your studio, I think you can be creative and use things that are on your desk to work with, right? And as we think about how this could become architecture, we developed a house for a developer in China, I should say a schematic design for a house, for a developer in China who wanted to use 3D printing at a resort called Jinhai Lake. And we proposed these 3D printed salt interiors that would be the more private spaces of the house, like bedrooms or offices, and a 3D printed cement exterior of the house, which again would be made out of cement blocks. And I guess we think about this or approach this a little bit differently than what's being done in China, because we don't see that 3D printing has to be one big gesture, right? You don't have to print the whole house in one shot. You can use different materials. And the buildings and the spaces that we live in and work in now are made out of many different materials. And components are the size that they are so that we can carry them and we can work with them. A brick fits perfectly in your hand, right? A nail is the size of your finger. So going forward, I don't think that we have to 3D print a giant house in one shot out of one material, but we can print components, and those components can be integrated with traditional materials. And this is a prototype of what that 3D printed cement facade would look like. And cement. So cement is the most ubiquitous building material in the world. And we have developed 3D printed cement. We've transformed it for the 21st century and for use in additive manufacturing. We've patented this process and we've tested it. Our cement has a compressive strength of 4,700 psi, You probably know from your structures class that cement at 28 days or concrete at 28 days is only 3,000 psi. So our 3D printed cement is actually stronger than traditional concrete, and it's translucent. We've experimented with different ways of finishing the cement. So here, for example, it's sandblasted so that it could be matte. We've experimented with different ways of connecting panels to make larger structures. This is Andrew Cutlass's P-ball. So here you can see all of the unique 3D printed parts come together perfectly, absolutely perfectly. And finally, another project at Fort Mason as kind of a proof of concept to show that the cement material is really commercially ready and viable. We designed a cement project called the seat slug, the form of which was inspired by the most recent species of sea slug discovered off the coast of California. And this is kind of our workflow, it's our process, you're probably familiar with it. Here we designed the base surface for seating. So it's 11 feet long and it's about 16 inches high, which is the right height for a lounge seat. And we thought about how we would deal with structure, so it's designed to be a series of arches. And then we distribute points along that surface, which you can see in these two models. And then we give those points depth, because we have to have panels or tiles or blocks that have depth so we can connect them together, right? And we do that with the floating point grid. And we further subdivide those points so that they fit within the build bed of the 3D printer. When we design a tile, we use the Karakusa method of tiling so that as that tile is repeated and rotated, they always match up, but you don't get a repeated pattern that's legible. And those tiles are then in Rhino panelized across that point distribution, which you saw in the previous slide. Here are all the 3D printed cement tiles laid out. And this is a rendering of the seat slug. It's not the actual seat slug, but it's important to show because the actual seat slug comes together with the exact precision shown in the rendering itself. And these are the 3D printed cement tiles, and you can see that everyone really is unique. They're all different. Here you see the depth, that offset from the point distribution, and we printed the holes in each tile so that we could mechanically fasten them together. We post-process all of our materials to give them strength. And there's the final seat slug. And more recently, we completed a project called Bloom, which is also made out of 3D printed cement. It's a tempietto, it's a celebration of 3D printing, and we did this in conjunction with a cement company called SCG in Thailand. They're the 6th largest cement company in the world, and they wanted us to develop their material for 3D printing. So this was one of the first times we've taken someone else's material and developed a formula for it, because they are interested in commercializing 3D printed concrete building components and selling them in Asia. So the Bloom, as we call it, is made out of 880 unique 3D printed cement parts. And the cement is white, unlike our cement. It's an iron oxide free cement. And it has a flower pattern cylindrically mapped onto the geometry of the tempietto, which is what makes each tile unique, because you see the bottom and the top half are the same formally, but rotated 45 degrees. But the flower pattern is what gives it uniqueness across the surface. And the flower pattern also allows for openings and light to pass through in really interesting and beautiful ways. Here you can see the 3D printed blocks themselves. And again, we 3D printed in the holes. Each piece is numerically coded, and the blocks at the bottom are 4 inches deep, and the blocks at the top are only 1 inch deep. So as you go up, the blocks get thinner and smaller and lighter. So here you can see the plan and how it is actually symmetrical from side to side, and how the top is the same as the bottom but rotated on that 45-degree angle. For structural integrity, because unlike the salty glue, there's no secondary support system. This is the interior. So from the interior, you don't read the leaf pattern quite as much, but you do see the structural grid. So each block that you see here is divided into 4 quadrants, and there's a structural grid or a cross inside each block, which gives it additional strength. And here's the new and the old together. So the 3D printed cement block of Bloom next to Worcester Hall at Berkeley. And we had to think about portability because this project is going to live in Thailand. So how could it be taken down and put back up with ease? How could it be shipped to Thailand? So we left each of the blocks connected into 4-foot by 4-foot panels that could be carried by one person and then assembled quickly on site. And again, looking back to look forward, in thinking about the design for the form of this, we were inspired by the Indabelli people and the forms that they used and the types of openings in their houses and the geometric patterns on the surface of their building. And one last project, Sol Grotto. This is a project that takes advantage of a material that I like to think of as neo-vernacular to the Bay Area. This project uses glass rods that were designed and engineered by Solyndra. Solyndra is a company that developed a solar tube that would ideally replace a solar panel. And the way it works is that there are 2 glass tubes, a 1/2-inch diameter one on the interior and a 3/4-inch diameter one on the exterior. And in between that is a thin solar film. And this tube could collect light from all different angles and reflected light from the roof and generate energy, so it didn't have to track the sun. But as you probably know, Solyndra went bankrupt.
Good evening, I'm Ken Bastuta.
I'm Dana King. Tonight, a CBS 5 exclusive. Remember Solyndra, the failed solar company in Fremont?
Well, Solyndra still owes American taxpayers $500 million, but we caught them destroying millions of dollars worth of parts. Elizabeth Cook with the video you'll see only on CBS 5.
Well, Solyndra will put its assets up for sale again next month, at least the assets they haven't yet destroyed. Look at what we found last week. At Solyndra's sprawling complex in Fremont, workers in white jumpsuits unwrap brand new glass tubes used in solar panels. They are the latest, most cutting-edge solar technology, and they're being tossed into dumpsters.
So they got busted, and they had to stop throwing away their assets. And they put out a call around the West Coast to artists and designers and invited anyone who wanted to come pick up the glass rods. So I drive by this company on my way to teach every day. So I stopped in and picked up some glass rods. And we decided these rods had a lot of potential and they were very beautiful and that we would be able to use them in a project at the Berkeley Botanical Gardens that we were designing for an exhibit called Natural Discourse, where artists and architects were asked to look at the relationship between the garden and the environment and the visitors. And so we built the Soul Grotto, which is inside this little wooden structure in the Botanical Gardens right in front of Strawberry Creek. And when you walk inside the Soul Grotto, you're greeted by 1,400 of the cylindra tubes, which are naturally glowing by the sunlight. And they glow this beautiful electric blue, even on a foggy, dimly lit day. And the form that